This part of the tutorial is devoted to in-situ array processing. As you'll already know, traditionally arrays are stored in files, not in databases. Currently, two key approaches exist. The first is to import files into an internal database format and then process. However, such import is error-prone and its time may exceed the processing time. The other approach is to process data in situ, that is, in their original file formats. However, most existing work develops dozens of algorithms almost from scratch for in situ array processing. ChronosDB implements a new delegation approach. It delegates file processing to well-known command line tools. The delegation happens by direct submission of files to a tool as command line arguments to process these files on a single cluster node. We avoid format conversions and get a powerful storage layer because these files are small databases. In addition, we get a rich set of optimized algorithms, but for a single machine. ChronosDB repartitions and streams input-output files between the nodes and tools to scale out the processing. We do really need to leverage decades of work on command line tools. For example, even the averaging runs several times faster when optimized properly. The idea sounds attractive, but what does it really take to realize? Well, you immediately face a myriad of challenges. Tools work on a single machine and pose special requirements for input files. We also have to work with complex file formats. Distributed computing is a requirement as we deal with big data. Let me present only a part of the resulting solution. Consider the following example. ChronosDB uses a command line syntax familiar for most users. ChronosDB command names and their parameters coincide with the names and parameters of well-known command line tools. You do not need to learn a new language. What is happening here? As input, we take two two-dimensional arrays, that is, satellite scenes with the spatial resolution of 30 meters per cell. First, we double the size of inputs by the interpolation, getting 15 meters per cell. Then, we compute the SAVI vegetation index using map algebra. Finally, we downsample the SAVI array to get a small, quick outlook array to be able to quickly estimate the result just visually. Let's have a look at the ChronosDB execution plan for the aforementioned query. As input, we will take two tiny arrays band 4 and band 5. Each of them has 4 subarrays separated by thick blue lines. This is the list of keys for subarrays of band 4. The key numbered 00 refers to the highlighted subarray of 2 by 2 cells. This is the list of keys for the array called band 5. The key numbered 00 refers to the highlighted subarray of 2 by 3 cells, not 2 by 2 cells. Although the key sets for both input arrays are identical, the shapes of some of their subarrays do not coincide. Hence, for now, it's impossible to delegate a binary operation like computing SAVI to a well-known tool, for example, GDelCalc. However, we first should perform interpolation. Let's interpolate band 4 and get red warp as a result. No materialization. To reduce runtime space requirements, wherever possible, ChronosDB uses virtual file formats, another exciting heritage from the file-centric world. The same for Band 5. Now it's time to prepare for computing SAVI. We will create a new intermediate array with the same subarray shapes as in Band 4. The basic idea is to cut each subarray of Band 5 into smaller pieces, assign each piece a key, and merge all pieces with the same key into a single new subarray. You see the first piece, which is cut from the original subarray with key 00, and that will go to the new subarray with the key 00 as well. Here is the other piece, which is cut from the subarray 00 and which will go to the subarray with the key 01. Let's continue cutting. Finally, we merge the pieces. Note that we merge two yellow pieces from different subarrays into a new subarray. Now let's cut again and finish the cutting. We call this two-phase retiling. Now everything is ready to compute SAVI. Subarrays of the same colors will be submitted together to the GDAL-Calc tool. Unlike interpolation, we have to materialize the SAVI array. However, subarrays will be placed to RAM-D. This is a virtual RAM drive. This allows the materialization of intermediate data to memory and, in the cloud, often avoids setting IOPS limits, which is very important for cloud settings. Here are the results: 00, 01, and others. The two-phase retiling and the computation of SAVI is a single array inner join operation. It's formally defined in the paper. Inner join is useful for algebraic computations on arrays. As you can see, it is significantly different from a traditional relational join. Now a unary operation follows, which is downsampling. The result will also go to a RAM drive if possible. However, this is still not the final result. Subarrays may grow too large or become too small during their processing. So how to control their sizes? The idea is to detect infeasible subarray sizes and to automatically insert the retiling into the execution plan to merge or split small or large subarrays respectively. In this case, all subarrays are merged into a single subarray. What about the performance? ChronosDB is efficient for complex analytic pipelines. With the aforementioned optimizations, ChronosDB outperforms SciDB by up to 47 times on this analytic pipeline. If we test resampling alone, be it upsampling or downsampling, we will discover that ChronosDB is up to 97 times faster than SciDB. Note that ChronosDB is not only faster, but it performs the real nearest neighbor interpolation. In contrast, SciDB just fills new cells with the values taken from the cells with the coordinates known in advance. Hyperslamming is one of the key operations for arrays. As you can see, ChronosDB is significantly faster on all types of arrays, which is a strong advantage. The hyperslamming performance depends on the chunk shape. However, SciDB cannot change array chunk shapes quickly. ChronosDB is over 300 times faster in switching to the right chunk shape. Chunking. You have already seen this slide in one of the previous tutorial parts, but I include it here for completeness. As you know, chunking is a crucial operation to tune array DBMS for better performance. ChronosDB is over 1000 times faster than SciDB.